Hello and welcome to my class, From Data to Decisions. I'm Chris Mack, your instructor, and this is Lecture 39 on the autocorrelation that we sometimes find in time series. Now, we're not really talking about time series analysis in this class. That's a very interesting subject. There's a lot of time series and lots of different ways of analyzing time series. But what we're really talking about here is an inadvertent time series that can sometimes creep into data that we're going to fit a model to. And so we're going to look for this inadvertent time series autocorrelation due to aging of the sample or drift in the measurement or some other time variation that's happening that we really don't want, that we really don't care about. It's not the purpose of our experiment. And so we're going to look at how to deal with that. We saw last time that one way of detecting such behavior is with a lag plot. If we have data which was collected in a time sequence and we've kept track of when the data was collected in that sequence, we can plot the ith residual compared to the I-1 residual. That is the previously collected residual. So we order them up in sequence, whatever that natural sequence is, usually time. And then we can plot the residual versus the previous residual in that list. That would be for a lag of 1. We can plot for a lag of 2 or a lag of 3 or anything else. So here's a run sequence plot where we show the residuals versus run number. It's sometimes a little hard to interpret that, but if we have that same data plotted in a lag plot, it usually becomes a lot easier. If we have just a random scattering about 0, about the middle, then we don't see any correlation between one residual and the previous residual. But sometimes, as in this data from Albert Michelson when he was measuring the speed of light a little over 100 years ago, we find that there is some correlation. So if I plotted the residuals, in this case the residual is simply the difference between the data and the mean data. If I plot the residual versus the lag 1 residual, I find that there's a general trend upward from left to right. This is a positive correlation. And we'll find that that's the most common kind of correlation that we sometimes see. So we sometimes want to be able to model this autocorrelation. So when something is correlated with itself, we call it autocorrelation. Sometimes the past is the best predictor of the future. And the next data point in time is related to, not independent of, the previous data point. So let's consider just one simple model of autocorrelation. There are, in fact, lots of interesting models that people use when modeling correlations. You may, at some point in time, need a more sophisticated model than this one. But for our purposes, just understanding the simplest model will be enough. It's called the first-order autoregressive model, and it frequently goes by the name AR of 1. 1 represents the lag, so we're only modeling a lag of 1. Our original model, our normal model, begins with this equation. yi equals some function of the xi's, that's the equation, plus random variable, epsilon sub I, the residual. But instead of assuming this random residual is normally distributed IID, independent and identically distributed for every I value, instead, we'll assume that the epsilon I is some function of the previous residual plus a random component. So there'll be, for each residual, there'll be a systematic and a random component, but the systematic component is a function only of the previous residual. So that's why it's AR1, autoregressive 1. It's autoregressive because it's a function only of itself in the past. And we're saying it's only a function of one previous time step. We'll then assume this random variable, u sub I, is normally distributed IID, and the parameter that we need to understand is rho. We call this the autocorrelation coefficient or the autocorrelation parameter. And like correlation coefficients, it's a number between -1 and +1. If rho is 0, I think you can easily see that this model reverts to the ordinary least squares model. It means there's no autocorrelation involved. If rho is positive, that means we have a positive autocorrelation or persistence. That is, whatever the past behavior is, the next behavior is going to be similar to it. It's persisting. If rho is negative, it means we're getting an oscillatory behavior. If the last residual is high, the next residual will be low. If this residual is low, the next one will be high. So it's bouncing up and down around 0 every other data point. That is rare. It just doesn't happen that much. There's not many physical mechanisms that give rise to that kind of behavior. But positive autocorrelation is in fact common. So what are the properties of this autoregressive 1, AR1 model? First of all, the properties of the error terms. Even though this error term, this residual, is a function of the previous residual, we still find that the expectation value of all the residuals is 0, just like we've had before. The variance of the residuals equals the variance of the random component, u sub I, that we assumed was normal, divided by 1 minus rho squared. The covariance between one residual and its previous residual is given by this equation, and you see it's the parameter rho times the variance. In fact, a correlation coefficient is defined as the covariance divided by the variance of square root of variance of each of the components. But since every component has the same variance, every epsilon has the same variance, we end up with this result. If I look at different lags than 1, if I have a lag of S, 2, 3, 4, whatever it might be, then the covariance of a residual and its S-lagged residual, 2 steps back, 3 steps back in time, is going to be rho to the power of S times the variance, as long as S is bigger than 0. Well, these are the properties of the AR1 model. Our questions, our two main questions that we're going to have to answer in this lecture are, how can we test for autocorrelation? How do we know when it exists and we need to worry about it? And then if we discover that autocorrelation does exist, how can we estimate the parameter rho? So first, testing for autocorrelation. The most popular test and the main test, the only test we're going to be using, is the Durbin-Watson test. It's basically a hypothesis test that begins with the null hypothesis that the autocorrelation parameter is 0. There is no autocorrelation. The alternative hypothesis will be that rho is bigger than 0. That's because we know that negative autocorrelation is rare, so we're really only going to test for positive autocorrelation. I'll show you how to test for negative autocorrelation in a minute, but generally we don't have to worry about that. We're going to do that with something called the Durbin-Watson statistic, which is shown here. So we take each residual, subtract off the previous residual. So it's the gap or the distance between two residuals, neighboring residuals. We take that quantity squared and we sum up all of those differences. We divide that by the sum of square errors, sum of all the residuals squared. What would we expect this statistic to be? Well, if we have lots of correlation, that means the next residual is a lot like the previous residual. These things are related. They're not independent of each other. These things are going to be very close to each other, and therefore their difference is going to be small. And we find that for a lot of correlation between residuals of lag 1, the Durbin-Watson statistic is very small. When the Durbin-Watson statistic is big, then we see a lot of correlation going on. Excuse me, the opposite. When D is small, we see a lot of correlation. When D gets larger, that means we get random variation. Sometimes epsilon I is bigger than epsilon I minus 1. Sometimes it's smaller. Sometimes it's similar. It's just random, and D is therefore a larger number. So if D is smaller than some critical value, we can reject the null hypothesis. Now, just a note, we are doing this entire test based on the raw residuals. The whole thing is set up using raw residuals. We're not using the externally studentized residuals or internally studentized residuals. Only the raw residuals are at work here. Now, what's the critical value for this statistic? Unfortunately, there is no exact critical value for D. Instead, people, in particular Savin and White in the paper below, have defined upper and lower limits for the critical values. What that means is you look up the upper limit for the critical value of the Durbin-Watson statistic D, and we find that when D is bigger than that upper limit, well, we can't reject the null hypothesis. That there is no autocorrelation. However, if D is less than the lower limit, and we do reject the null hypothesis in favor of the alternate hypothesis. And unfortunately, sometimes D turns out to be between the upper and lower limits, in which case the test is inconclusive. It's not quite the same as saying we can't reject the null hypothesis. It's obviously not the same as saying we do reject the null hypothesis. It's just saying, I'm sorry, this test is not conclusive. So what do we use this test for? How do we use it? Well, first thing to note is that this test only checks for an autocorrelation with a lag of 1. If you have longer lags, those might not be detected. Only lags of 1 are being tested here. That's okay for us because we're really only going to worry about the AR1 model. Approximately, this statistic, D, the Durbin-Watson statistic, is 2 times 1 minus estimate of the autocorrelation parameter. So rho's autocorrelation parameter, rho hat, will be our estimate. Talk about how to estimate that in a moment. But basically, D is 2 times 1 minus rho. So when D is about equal to 2, no autocorrelation. When D is getting closer and closer to 0, then we're approaching perfect autocorrelation. So that's kind of the range we look at. When D is getting close to 2, then we know there's no autocorrelation. As D gets smaller and smaller, we see more and more autocorrelation at work. We can test for negative autocorrelation. Rho is negative, and we see that D is bigger than 2. So we can test for that too. The way we test for that is by creating a new test statistic equal to 4 minus D, where D is calculated in the normal way. When we do that, we have the exact same test that we can do. We can use the Durbin-Watson critical tables as before and do all of our testing exactly the same. But this time we're testing with the alternate hypothesis being that rho is negative. All right, what are the consequences of autocorrelation? We've done a test. Durbin-Watson says, yes, there is autocorrelation in our residuals. What does that mean? How does that affect our regression? Well, it turns out the regression coefficients that we do that we get when we do an ordinary least squares regression are still unbiased. So that's a good thing. We have unbiased regression coefficients. However, they are no longer the minimum variance estimates, and our estimates of the mean square error of the residuals and residual variance will be smaller than the true value. We're going to underestimate how much variation there is. We're going to think our model is doing a better job than it really is. The standard errors for all of our regression coefficients will be too small. Statistical tests, such as the f-test or the t-test, that we might do on the model or on model parameters, well, they're just not going to be that good. They're not going to be very accurate because we're underestimating the standard errors of all the coefficients. and in particular underestimating mean square error of the model for the residuals. So if we care about these things, and we should care about these things, then we need to do something about autocorrelation if we find it. To do something about it, we need to estimate the rho. So we've run the Durbin-Watson test. We've detected autocorrelation in the residuals. So we want to estimate rho. There's three common ways, three ways that people do this. One is we look at the lag plot and we fit a straight line. Look at the slope. Our straight line should be a straight line through the origin. So we run our regression, setting the intercept, forcing the intercept to be 0, and then we grab the slope out of that. The other thing we could do is calculate the correlation coefficient between the residual and the lagged residual. But the correlation between these residuals and residuals lagged by 1. This is the preferred approach. And this is the approach we'll use in this class. Alternately, we can use this equation here, R prime. So you'll see some people in the literature using this equation. All of these things, which is you might see is like a covariance, estimate of the covariance divided by the sum of square errors, the estimate of the variance. These are almost all exactly the same. They're just little bitty differences. The differences have to do with the endpoints, the first and the last. Right? When I'm looking at residuals with the lagged residuals, you see that we are missing some information about the first and the last data points. We only have n-1 comparisons to make, not n comparisons to make. So the slope is about equal to the correlation coefficient R with this little error term, difference between first and the last residual squared divided by 2 times the sum of the square errors. R prime is similar, except for it's the average, not the difference between first and the last residual. Notice that the slope can be either higher or lower than the correlation coefficient rho, but R prime is always smaller than the correlation coefficient. Here's an example. All these things are very easy to calculate. We have built-in functions to do correlation coefficients and slopes and stuff. So here's an example. This is from some flow meter data we've looked at before. It's in dataset 2, which you'll find on the website of the course. And we fit it to a model, and we got the residuals. Look at the residuals versus lag 1, and we see this correlated behavior. If I fit a straight line to this residuals versus the lag 1 residuals, I get a slope of 0.47. When I do a correlation between these two columns of data, the residuals and the lag 1 residuals, I get 0.923, so a little bit lower. And if I do this R prime calculation with this formula, I get something lower still, 0.85. All of these are reasonable. And if we used any one of these, it probably wouldn't affect the answer too much. But we're going to use the correlation as our method of estimating rho. Now, we're about to embark on a correction of correlated residuals using the AR1 model. But the first thing we should check is whether the AR1 model is even appropriate for this data set. How do we do that? How do we check it? Well, we do that by calculating something called the autocorrelation function, or ACF. This is nothing more than the correlation coefficient for different lags. So the correlation coefficient for a lag of 1 gives us a certain number. If we use a lag of 2, we can calculate a correlation coefficient between the data residuals and the residuals lagged 2. We keep doing that for all of the different lags out to some number, and we can plot the correlation R, autocorrelation coefficient R versus lag. And the question is, does it look like an AR1 model? Well, what does an AR1 model look like? An AR1 model says the correlation coefficient of a lag of k is the correlation coefficient for a lag of 1 to the kth power. In other words, it should look like an exponential decay. Is that what this looks like? Well, the first number is 0.5 or something. The next number is a little less than 0.2. Well, that's about 0.5 squared. A little bit lower, but not much. And then it kind of levels out near 0. Of course, it's not exactly 0 because there's some sampling error. And so these values close to 0 are within the uncertainty, the standard error, these coefficients. And so AR1 is probably appropriate for the Michelson data. Here's another set of data that you'll find in the data spreadsheets on the course website. This is sunspot data. This is the number of sunspots detected over time. And what we find here is a very different autocorrelation behavior. Look at how it swings down, goes negative, swings up, goes positive again, swings down, goes negative again, swings up, and it oscillates and eventually levels out to 0. This is like a sync function or something like that. Well, this oscillatory behavior comes from the fact that the sunspot data itself is cyclical. AR1 is not an appropriate model here. In fact, we have a periodic variation, and we need to have some periodicity in our model in order to capture this behavior. So if we saw that kind of behavior, we would kind of give up and say, well, the techniques we're studying so far are not going to help us here. In this case, sunspot data, you might guess, you really do need a time component, periodic time component in the model. So how do we fix these autocorrelated residuals? Let's see where we're at. On the Durbin-Watson test, we found that the statistic allows us to reject the null hypothesis that rho equals 0. We estimate rho by looking at the correlation with a lag of 1. And now what do? The first thing is to check the model. Remember, a couple of lectures ago, I said the easiest way to create autocorrelated residuals is to have model error. A missing predictor variable, it will very frequently show up as autocorrelated residuals. This is especially true if you did not randomize your experiments. If you didn't randomize the order follows a natural order of a regressor variable, and you're going to add an artificial time dependence to your data just by having the wrong model. So the first thing you do is try to find that behavior and fix it. But if you've randomized or if you've proven to yourself that that's not what's going on, if the autocorrelation function is caused by drift or aging or some time dependence that's in your model, in your data rather, and you don't want it in your model, you want to separate this drift, this aging, this time dependence from the rest of the things that you're studying, there's two ways you can do that. One is try to eliminate the drift and the aging and the other behavior. Look for what's going on in your experiment. Find out why the measurement is drifting over time. Maybe there's some calibration you can do. Calibrate more frequently. Maybe you can make some adjustments on the tool to prevent that drift. If it's sample aging, maybe you can get new samples, or you can use a technique that doesn't age the samples as quickly. Try to eliminate time dependence from your experiment. But if you can't do that, there's a last resort approach. The last resort is to use the autoregressive model to separate out time dependence from the functional fit, dependence on regressor variables other than time. And that's what we'll do right now. The first order autoregressive correction goes like this. Let's suppose we just have a linear model, straight line model. So my model is B0 plus B1 times X. Well, again, this looks exactly like ordinary least squares regression for a linear straight line model, except for now we're going to create a model for the residuals that is the autoregressive 1 model. So it's saying the residual equals rho times the previous residual plus a random IID normally distributed random variable. We're going to eliminate the autocorrelation by transforming our variables. We're going to transform each of the variables x and y by subtracting off rho times the previous variable. So yi is the ith y data point, xi is the ith input variable x data, and I'm going to create transformed yi prime and transformed xi prime by taking yi and subtracting off rho times the previous yi. Xi prime, xi minus rho times the previous xi. Once we've transformed these variables, we can show that we're also transforming the slope and the intercept. In fact, the slope remains the same. It doesn't change the slope at all, but it will change the intercept by an offset amount, 1 minus rho. So now we have a transformed model, and look, the epsilons have disappeared, and the only thing in the model now is the ui, and the ui, it's our ordinary least squares assumption, normally distributed, independent random variable. With our transformed y's and our transformed x's, we perform ordinary least squares regression. We get estimates of beta 0 prime and beta 1 prime. From the estimates beta 0 prime and beta 1 prime, we have estimates for the standard errors of beta 0 prime and standard error of beta 1 prime. We can transform back to our original model. We can get our original intercept, B0, our original slope, B1, with new standard errors, each of them as well. R is our estimate of rho that we obtained previously as we discussed. The final model will have both the functional how does y depend on x behavior, but also built into it how does y depend on the previous value of y. This then becomes our final model, and you see that it's got 3 parameters, not just 2. Intercept and slope, but also r. And because we were able to do an ordinary least squares regression, because the assumptions of the ordinary least squares regression are now true, they're correct, we can have confidence in standard errors, our confidence intervals, etc., that we put around our coefficients and our predictions. All right, last thing. Suppose you go through that process. Durbin-Watson statistics says you're autocorrelated with lag of 1. You estimate rho using the correlation coefficient. You then create a transformed model, the transformed model using ordinary least squares. What do you do next? Well, you need to check to see if you really did get rid of all of the autocorrelation behavior. So new residuals, go back to here, new residuals of our model. These residuals, we hope, we're assuming, are identically distributed and independent normally distributed residuals. Let's test that. We do the Durbin-Watson test again on the new residuals to make sure that it does not fail, does not reject the null hypothesis that rho is 0. If it does, we can iterate the whole procedure again. Or we can go back and try a larger value for the correlation coefficient and see if that fixes the problem. So we can play around with the correlation coefficient until we get a Durbin-Watson test showing that there's no correlation left. This is called the Cochran-Orcutt procedure, where we iterate multiple times until we converge to residuals that truly are uncorrelated. Some alternative approaches, just pick a really large value of rho, close to 1, and try it and see what happens. If your first time you do it, you get these residuals that are still correlated, try a much bigger value of rho, see what happens. Or a more sophisticated way would be to use a maximum likelihood estimator of rho that is determined at the same time when you're fitting model parameters, the regression parameters for slope and intercept, for example. This requires a nonlinear regression. It's a little more difficult to do, but if you did that, you have your best estimate of rho and model parameters simultaneously. All right, let's see what we have learned in Lecture 39. As always, you should be able to quickly and easily answer these questions. What is an AR1 model? What is the Durbin-Watson test? What is the Durbin-Watson statistic? And what can it tell you? How can we estimate the correlation parameter rho of an AR1 model? And finally, how do we correct for autocorrelation when doing a regression if we detect that it exists in our residuals? Well, that's Lecture 39. Our next lecture will perform some of these calculations, Durbin-Watson test and transformation of our model in Excel and in R. Till then.